Hello everyone, Harry here. Welcome to Scrap Science. Throughout the history of this channel, Scrap Science, you may have noticed that I've been on a bit of a quest, and that quest is to do every single experiment that I can think of that involves electrolysis. I deviate from this quest sometimes, but I'd say around 90% of my videos are probably electrolysis experiments or preparation for electrolysis experiments. Anyway, you know this, and we're not really going to be doing anything different today. I want to make some bromate. We're going to make the bromate ion by electrolysis of a bromide solution. From a practical standpoint, this is not going to be much different to the videos I made about chlorate production, potassium chlorate and sodium chlorate in particular. So if you haven't seen them, I would recommend going and checking out those videos just to get an idea of what we're actually doing. I'd quite like to keep the introduction to this video quite brief. We're going to quickly introduce the cell, we're going to set it up and get it running, and then once that's all done, we're going to start explaining the reaction that we're actually doing today. I've spent the last couple of days building a bromate cell. This is just out of a jar that I got from the supermarket, 300 milliliter jar. It doesn't need to be too big because I don't need all that much bromate for future experiments. What I've got is what will hopefully seal over the top of this jar that will fill with bromide solution. Some gas takeoff tube, 2 electrodes, one being platinum, that'll be the anode, and one being titanium, that'll be the cathode. I've chosen a titanium cathode because it's particularly inert. It makes a really good cathode when we're doing electrolysis of oxidizing solutions. Not the most efficient choice, but it will get the job done definitely. The square in the back is our platinum anode. I've chosen platinum just because I have it basically. Platinum will not degrade in the electrolysis of bromide solutions, so we can run this cell without worrying about electrode degradation or disintegration. But technically speaking, it's perfectly acceptable to use a graphite or carbon electrode as the anode in this case. From what I've seen, most MMO anodes also work for bromate production, but if they are coated on a titanium substrate, sometimes you can run into issues of the titanium underneath oxidizing. This only really happens if you've got bare titanium exposed, as far as I can tell, but something to be cautious about if you're going to be using MMO. Anyway, for those reasons, I'm using platinum because I can and I want to. This will basically just sit on the top of this cell here like this, and the electrodes dip down into the jar like that. In preparation, if we open this back up, I have prepared a couple of 100 milliliters of sodium bromide solution. It still hasn't dissolved. I've tried dissolving 160 grams of sodium bromide in this solution here. It's taking forever because I recently moved lab spaces. This is my new lab space, and I don't have a hot plate yet. So this has taken hours and it's still not dissolved, but I don't really care. I'm sick of waiting and it's gonna go straight in the cell. Yeah. That chunk of salt will hopefully slowly dissolve over the first day or so of the cell running. With a bit of PTFE tape to make sure the lid seals on properly. And with our cell sealed, our electrodes hooked up, and hopefully a correct connection to our power supply, and also hopefully a good view of the electrodes, I shall turn up the voltage and the current, and hopefully we'll see something happening. Ooh. I think something's happening there. I'm going to try for 0.8 amps. Oh yeah, that's exciting. I didn't quite expect the color to be this strong, but that orange stuff that you can see falling off the platinum anode is effectively elemental bromine, or it's the tribromide ion that results when elemental bromine encounters bromide solutions. The bromine, or the tribromide, I suppose, is an intermediate in the formation of bromate, so this is exactly what we expect to see. On the titanium cathode, we're getting hydrogen bubbles, but I'll talk more about the actual reactions that are happening when we do our full discussion of the mechanism of the reaction we're doing. Overall, seems to be working, so we'll let it do its thing. A week has now passed since I started running the cell. I've been running this thing at a current of 0.8 amps this whole time. Looking at the cell, you'll notice maybe three differences or three things happening since we started. Number one, we have very clear separation between a red layer and a much clearer layer on the top. This is the bromine or tribromide that forms on the anode, sinking to the bottom of the cell. As I mentioned before, this is an intermediate in the reaction that forms bromate, so we expect this to occur. Because it's so heavy, we get this really cool layering effect where the solution actually looks like two different liquids. It's not really a problem, provided we can periodically come in and mix things around and get the two layers to react together. This mixing step should actually be the part of the reaction that forms the bromate ion. The second thing you might notice when you're looking at this cell is that there are a bunch of crystals forming at the bottom of the jar. I find it kind of hard to believe that these are bromate crystals for reasons that I'll reveal in just a second. Instead, I'm pretty sure these are just sodium bromide crystallizing out because it has been really cold here lately. Third thing, number three, most important thing, is that there are hardly any bubbles forming on the cathode on the right there. This is a little bit confusing because we're running the same current as before, 0.8 amps. The only way this can really make sense is if our current is now driving a different reduction reaction on the cathode, one that doesn't generate gas. This reaction is actually the reduction of our bromate and our intermediate bromine species to regenerate bromide in solution. Basically, the cathode is now undoing all of the hard work we're doing on the anode. Anyway, we obviously need to stop the cathode from destroying our hard-earned product using a cell additive that suppresses the back reduction of our oxidized bromine species and doesn't really affect the production of hydrogen. This additive, in my case, is the persulfate ion. Dichromates also work and they're more common to use, but I don't really like dealing with chromium waste. This here, hopefully you can see in the bottom of this beaker, is some potassium persulfate. It would be good if we had the sodium salt, but the potassium one is just so easy to crystallize out of solution, it was easy for me to make. I'm going to turn off the cell briefly, we're going to pull it apart and then add this to solution, and it should bring our efficiency back up. A little later, the persulfate additive didn't really work as well as I'd hoped. So what I've actually done is I've added just 100 milligrams or so of potassium dichromate instead as an additive. I know this one works. So hopefully when we turn this thing back on, we should see a bunch more hydrogen generated. Looks pretty good to me. Once again, you can see the bromine species falling off the anode, hydrogen coming off the cathode, a whole bunch of it, and we've got quite a good rate of bubbling through our sodium hydroxide bubbler. Anyway, with our efficiency back up to what we want it to be, I think now it is time to talk about the mechanism of the reaction. Now, with slightly better audio quality, I'm going to do my best to try to talk through this reaction. It might be easy to assume that it's exactly the same as a chlorate cell, which I've covered in the past, but there are some differences here that actually make the bromate cell easier to run than the chlorate analog. In fact, I find the bromate cell really quite satisfying because there are a couple of things that line up just perfectly for the bromate cell to run rather efficiently without much effort. To start with, we should probably briefly recap how a chlorate cell works, and then we'll be able to compare that to a bromate cell. If we were to electrolyze a saturated solution of chloride with inert electrodes, as I've done in other videos, we would first see that the easiest reduction half reaction to do on the cathode is this one, the reduction of water to make hydrogen. And the easiest oxidation half reaction to do on the anode is this one, the oxidation of chloride ions to make chlorine. Basically, we're making hydrogen gas on the cathode and chlorine gas on the anode. If you look closely at these reactions though, you'll see that the cathode actually generates a byproduct, hydroxide ions. Obviously, as we make more of these, the solution in the cell becomes more basic, to a pH of 9 or 10, where chlorine can no longer escape the solution as a gas. This happens quite quickly, and under these conditions, the oxidation of chloride ions on the anode results in the formation of hyperchlorite ions, like this. Letting this happen for a little while, we'll start to get an appreciable concentration of hyperchlorite ions. And there's two ways the reaction can proceed from here. An inefficient electrolytic process or an efficient disproportionation reaction. We're going to talk through both. First, if we let the hyperchlorite concentration continue to increase, we'll eventually get to the point where they are oxidized to chlorate on the anode by this reaction. Analyzing this whole process of going from a single chloride ion to a single chlorate ion, we require the passage of 9 electrons through the cell to do it this way. Alternatively, if we set up our chlorate cell with some fancy pH control and raise the temperature, we can force the hyperchlorite we generate to simply disproportionate into chlorate and chloride. Maintaining a pH between 6 and 7 will protonate some of the hyperchlorite, and at higher temperatures, maybe 60 to 70 degrees Celsius, this disproportionation reaction occurs. Under these circumstances, the overall process of going from a single chloride ion to a single chlorate ion requires the passage of 6 electrons through the cell. Much more efficient, but the pH and temperature control is more difficult to perform. I've never gone to the effort. Bromate cells can follow an analogous set of reaction pathways, so we can start talking about them now. Starting with a saturated bromide solution, electrolysis with inert electrodes results in the reduction of water to give hydrogen on the cathode, and oxidation of bromide ions to give bromine on the anode. Bromine is actually rather soluble, especially in solutions of bromide, so we don't really lose any here. Now, like we described before, the byproduct of hydroxide ions on the cathode works to make the solution more basic over time. Just like the chlorate cell, we get to the point where the anode oxidizes bromide ions to hyperbromite ions instead of bromine. Actually, that's not quite true. This one's a bit more complicated since the solubility of bromine and tribromide results in an equilibrium with hyperbromite, so we can still oxidize some bromide to bromine. But anyway, we are effectively making hyperbromite here. And with more and more hyperbromite in solution, we have our 2 reaction pathways like last time. First, we could oxidize the hyperbromite on the anode to give bromate like this, analogous to the 9-electron process from before. Or we could protonate some of the hyperbromite and proceed via the disproportionation route like this, analogous to the 6-electron process from before. Luckily for us, the pH range over which hyperbromite ions can be protonated is quite a bit higher than for the hyperchlorite. In fact, the ideal pH for this is actually pretty much spot on the natural equilibrium pH for this electrolysis, 9 to 10. For the chlorate cell, it was 6 to 7, requiring an adjustment of pH to get it to work, but here we don't really need to do any adjustment at all. Additionally, the disproportionation reaction with hyperbromite is about 100 times faster than it was for hyperchlorite, so we don't even really need to raise the temperature, though it wouldn't hurt. As a result of all of this, the efficient 6-electron process is the dominant reaction in a bromate cell, and the inefficient 9-electron process involving a second electrolytic oxidation step is a minor reaction. So the bromate cell runs at a pretty high efficiency without any extra help. And to make things even better, using sodium bromide as our starting material allows our sodium bromate product to crystallize out easily, since sodium bromate is less soluble than the bromide. Everything just works really nicely here, and I really like it. Anyway, that's it for the mechanism. I hope I've conveyed how everything is kind of working in our favor here. Bromate cells are nice. Nearly 4 weeks after beginning our electrolysis, you can see we've now formed quite a nice amount of what I assume is sodium bromate in the bottom of our jar. I calculated previously that at our desired 0.8 amps running through the cell to perform this electrolysis, we would have only needed about 2 weeks of electrolysis to completely convert all of the sodium bromide that's in there into sodium bromate. I've left it running for 4 weeks because for quite a bit of that time, we haven't had 100% efficiency. We also haven't had the full 0.8 amps that we wanted. With the amount of solid that I can see in the bottom of the jar though, that is way more sodium bromate than I'll ever need. So I think I'm happy to stop the cell running right here. Well, the crystals were much more difficult to get out of there than I thought they'd be, but they're now all in this beaker, and the plan from here is just to heat up the solution, get everything redissolved, and then as it cools down, we'll get some new, nice, smaller crystals that are not all clumpy like this of our sodium bromate product. Anyway, to the hot plate. While that's heating up, let's see if we can get our electrodes out of the cell. A Teflon platinum electrode comes out very nicely, of course. Well, our seal and our lid held up a lot better than I expected. There's a bit of corrosion there, but that is kind of what's going to happen when we're dealing with bromates or oxyhalogen species. And with the electrodes rinsed, if we have a look at our titanium first, you can see a slight amount of discoloration on the surface that was actually performing the electrolysis, but this is, it's titanium. We're not really going to care about this tiny little piece. The platinum still looks shiny and new. It seems to be coated a little bit in some sort of surface film. I'm pretty sure that will clean right off though. Basically, both electrodes have fared pretty well. We could probably reuse them a great number of times if we wanted to make a whole bunch of bromate. These few steps that we're doing here aren't all that complicated. Just to do a recrystallization, we are dissolving everything up by heating up the solution, and then we crystallize our bromate product back out as we cool the solution down. And with our nice clean crystals of our pure sodium bromate, we can filter them out and give them a bit of a wash. And after drying, this is it, 93.8 grams of sodium bromate. It is very nice and pure because I've been extra careful to keep our crystals of a high purity. I could have gone for yield by crystallizing out more from our actual cell solution. In fact, there's probably as much as maybe 50 grams of our product left in solution. But for the purposes that I need sodium bromate for, I don't need much of it, but I need it to be very pure. So that's exactly what I've gone for here. Considering the fact that we were able to crystallize out 93.8 grams of our product, I will put our overall yield from our original sodium bromide on the screen right now, and also our Faradaic yield from the actual electrolysis. Anyway, I'm going to go ahead, take this away and store it very nice and safe for a very special project later on. And I guess the only thing left to do is actually test our product to prove that we have actually made the thing we were expecting to make. And that's that, basically. We have made a bunch of sodium bromate from our bromate cell. I hope you enjoyed. Please do let me know what you thought of the part where I was explaining the reaction. I'm kind of planning on doing a whole bunch more animations like that of the mechanisms of the reactions that I do in the future. So let me know what you think. And with all that said, that kind of concludes everything. So see you later.